this really is the last part of organic chemistry. And so it's polymer chemistry. I'm going to get into it right now. So your polymer chemistry, as you can see, their polymers are large molecule. We say macro means large, made up of a small repeating unit or a small repeating unit called monomers. I tend to say that the word poly means many, and the word poly means many, of course. Mono means one, right? Mer, I say mer means unit. Okay, but I'm not sure if that is even anywhere. I've never really checked. But anyway, so your polymer is many units and your monomer is one unit. So your polymer is made up of this repeating unit, this one unit which repeats over and over and over until you get millions and billions of molecules. Now, there are two general classes of polymers, as you can clearly see on the paper. You have natural and you have synthetic. Natural polymers, I would say, are God-made. Synthetic polymers are man-made polymers. Okay? And so we can further divide our polymers into condensation polymers and addition polymers right there. Now, your addition polymers, the ones that you're expected to know, right? They tend to be man-made. These are the polyvinyl chloride, which is PVC, polythene, which comes from polyethylene, polypropene, and polystyrene, which we call styrene. Okay, these are the ones that we need to know about. These are made from, as it says there, free radical mechanism. You do not need to know the mechanism really. In the past, you used to have to know it, but no, you don't have to know it. So therefore, now what I'm going to show you is the general structure of the alkene, because these are alkenes, as you can see, from the double bond there, if you can recognize that. So I'll show you the general structure of the addition polymer. So this is what it looks like. You have a carbon, double bonded to a carbon, bonded to a hydrogen, bonded to a hydrogen, bonded to a hydrogen, and then bonded to R. Now, R can be hydrogen, it can be CH3, it can be chlorine, or it can be C6H5. Okay, now, so these are the four polymers. Now, if R is hydrogen, then this molecule becomes ethene, and the polymer made from that is going to be polythene or polyethene. See it right there, this one. Okay, polyethene or polyethene. Now, if R is CH3, then what you would have happening is that there are 3 carbon atoms in the chain. So you know that is propene, and so you would make polypropene. If R is Cl, so if you switch out R and R becomes Cl, then what you're going to end up with is PVC, polyvinyl chloride. So vinyl chloride, first of all, your monomer would be vinyl chloride, and when you polymerize it, it becomes polyvinyl chloride. Okay, so those are, and then finally, if R is C6H5, then that is styrene, and then when it combines, you get polystyrene. Okay, so those are your mono, and these are skeletal structures right here, of course. So this would be this would be ethene, C double bond, and this is a H, this is a H, this is not a smiley face, it's a H, and that's a H. Okay, hold on one second. Okay, so yes, so that is your ethene, which is going to make polyethene, and then below that you can see your PVC. Let me clear all drawings, right? So down there says your PVC coming from vinyl chloride. So this section here in the middle, really, this is a carbon, this is a carbon, and this is the double bond between them, and that's your chlorine and that's your hydrogen. So that's vinyl chloride. All right, then now this is your polypropene. This is this right here, this section, this is a carbon. Okay, and this would look like this. I just want you to see clearly. So this would look like this. It may look strange, but that's what it looks like. Okay, and this is double bond, of course. So that's what it looks like. And this right here, this is this. Okay, so that's your propene. And then now you have your, what was the other one? You have the next one, which is polystyrene. And there's your styrene, C6H5. Each of these points in the hexagon is a carbon atom. So that's, you can clearly see it's 6 carbons since it's a hexagon. And then attached to each carbon is 1 hydrogen. Okay, so C6H5, and that's styrene. So all your examiner tends to ask you a question which looks like this. They would say, okay, ethene is a monomer that combines to make polythene. Show 3 repeating units for the combination of ethene. 3 repeating units. So what you need to know, say, okay, ethene, this is ethene, right? And I'm talking to myself now in talking to you. So this is ethene, right? And it's going to polymerize. What would 3 repeating units look like? First of all, ethene has 2 carbons. So 3 repeating units would have 6 carbons. So you're supposed to now draw 6 carbon atoms like this. Okay? So that's your 6 carbon atoms. And then now you say, all right, that's our 6 carbon atoms. What you need to do now is put an N right here to show that those carbon, the number can be more than 6, and it can be up to millions and billions. And you need to put in your hydrogen. So all of these lines right here represent hydrogen atoms bonded to the carbons. Now notice something here, right? You actually broke the double bond in the monomer to join it together to form the polymer. So the double bond breaks, okay? And that's what, this is what 3 repeating units of polyethene would look like. If they ask you for, polypropene, then you simply change this to C. Let me change the color there. You simply change this to CH3 and you alternate the CH3. So this is CH3, then you have hydrogen, then you have CH3, then you have hydrogen, then you have CH3. Okay, so you alternate the CH3s. If it's polyvinyl chloride, you change the CH3 to Cl. If it is polystyrene, you change the CH3 or the Cl to the CH3 to the C6H5. Okay, and that's all. Your examiner will just ask you about that. When we go on further, you'll see more questions that the examiner may ask. All right. So here we go. Give 2 uses for each of the above mentioned polymers. So what are the uses of these things now? Polythene. Polythene is used in plastic bags. I don't know if you know those clear plastic bags, right? The ones that they sell seasoning at shops. That is polythene. That is a polythene bag. If you look at it, it's actually called poly bags. If you look at the label, it says poly bags because it's polyethylene. So it's used to make plastics. That's one thing. And of course, yeah, well, it's usually used to make plastics, really. PVC is used for piping. The white pipes that you see being used in your house, that's PVC, the white pipe. You know what I'm talking about, yes? Hello?
Can't hear me, sir? Hello?
Are you hearing me?
Yes, sir, I'm hearing you.
You heard what I asked?
Yes, sir. You said if I know what a PVC is, I said yes.
Okay, so you know the PVC, that's what PVC. And of course, PVC is used for piping. It's also used for electrical purposes. When they're building the houses, they put the electrical wires through them. So it's used for that. It's a non-corrosive material, and of course it can last long. And that's why they use it. Polypropene, you may not know this, but not polypropene. Polypropene is used to make plastic bags as well. So remember I spoke about the poly bags, which are the clear bags. Black scandal bag, even though they have banned plastics now. Black scandal bag and white scandal bag and all of these things are polypropene bags, okay? Those are polypropene bags, right? So these things are usually used to make plastics. You can simply look on the internet and see these things. Anyway, polystyrene is used to make styrofoam cups, which is an insulating material. Before they banned the plastics and all of these things, when you wanted to drink soup, you'd get the soup in a styrofoam cup, which was an insulating material. And when you used to buy box food at school, you used to get it in these white containers, the styrofoam boxes. That is polystyrene, you know. Okay, and that's what polystyrene is used for. Okay, so we will proceed even further. Condensation polymers, these tend to be God-made. I wrote that specifically, but there are a few man-made. So nylon is man-made. See right there, nylon. Nylon is man-made. Okay, so nylon is a man-made polymer. Proteins, fats, and carbohydrates will also be studied, and those are actually God-made polymers. So nylon, it is a synthetic polymer. Synthetic means that we man-made it. Condensation polymer, it is considered a polyamide. So let us dissect what is being said here. Synthetic means that it is a man-made polymer, and it's made by condensation reaction. What is condensation reaction again? Try to remember. I think I did say this. Condensation reaction occurs where you have two things coming together. So you have A being bonded to B to make AB. When AB come together, water is usually formed, or some other small molecule like nitrogen or something like that. But it's 99% of the time water. So that's why in some books you will see condensation reactions being defined as the combination of two species with the production of water. So the combination of two species to form a new species and water. It's not always water. It's only 99% of the time. But anyway, so that's a condensation reaction. Now we want to look at how nylon is made. So what they do is they take, well, sorry, it is a polyamide. And I'm going to show you what that is now. So what they take is an amine, which you really don't know that much about. And I'm just going to shorten the formula of the amine. So you have R, N, H, H right there. This NH2, this thing right here, this is the amine functionality. And let me explain what I mean by that. In organic chemistry, you have many organic compounds. One class of compounds is a thing called amines. Okay, their functional group is NH X, where X can be 1, 2, 3, or sometimes even 4. Okay, so this is an amine. On the other side of this R group, you have C double bond O OH. So you have the acid functional group. That's an acid. So what happens with your polymer now is that you have, this is your monomer. So this is your repeating unit. And of course, you're going to have the repeating units join. So you have the acid portion over here, HO, C double bond O, R, N, H, H. Okay, and here now what you have happening here is that you have water being formed. So your water is going to be H2O like that. If you notice, this is H2O, and you remove that. Now the product of that now, I'm just going to write the product down here now. You end up with R bonded to nitrogen, which is hydrogen there, bonded to carbon, double bonded to oxygen, bonded to R, bonded to N, H2, let me just write NH2, and over here you have COOH. Okay, so let's just look at what we have here now. All right, so you're not confused. We have a monomer. This is the monomer. Okay, that's the monomer. It is then combining with another monomer over here, and water is supposed to be produced. So we're taking water out of it. See there, 1 hydrogen, 2 hydrogens plus the oxygen. So this is your water. When you remove the water, the nitrogen over here is going to become bonded to the carbon over here. And let me highlight that down here so you can clearly see it. Okay, so this is the bond that was formed. This right, oh, let me use my hand. This is the bond that was formed right there. See there? Nitrogen bonded to carbon, which is double bonded to oxygen, and this is a hydrogen. Okay, now this bond is what we call the amide bond. Your examiner may ask you to identify it in a molecule and state its name. Okay, it's the amide bond. Let me draw it up here. N bonded to hydrogen, bonded to carbon, double bonded to oxygen. So that's your amide bond right there. That's it. Recognize it. Okay, so notice that nylon has an amide structure, polyamide structure. So what would happen now is this. Notice, let me try and clear this a little bit. Notice here now, let me clear that. Notice now down here that we have two monomers now. So this is a dimer. Di means two. So you have two polymers right here, two monomers joined together. What can happen now is that another monomer could join over here and another monomer could join over here. Okay, and it will continue to join and join and join and join and join until you have made whatever you want to make. Okay, and so this is how your polyamide for nylon would look. All right, so let us look at the next polymer now. The next polymer is proteins. Now look at what it says about proteins. It says proteins are from amino acids, which are monomers. The amino acids are the monomers, and proteins are polyamides. You see that? So proteins and nylon have the same structure. They have the amide functionality. Okay, so they have that link right there. So I'll show you now how you get your protein. Okay, so you have two amino acids, and there are about over 20 different amino acids. I'm just going to show you the general structure of an amino acid. So you have your carbon, which is double bonded to oxygen, bonded to hydrogen over there. Then you have another carbon, which is bonded to R and bonded to hydrogen. And then you have the N bonded to H, bonded to H. Okay. Now, what happens now is that you have another amino acid. The R up here can be a lot of things. It can be hydrogen, it can be a ring, it can be a whole host of things. You don't need to know those things. All right, all you need to know is that that's an amino acid, and here is another amino acid over here. Okay, bonded to a carbon, which is bonded to a R group, which is bonded to a hydrogen, double bonded to oxygen, double bonded, single bonded to that. Of course, this is a condensation reaction, so you're trying to remove water. So here is our water, H2O. Now, I could have taken out this hydrogen. It doesn't matter as long as you take out water. So that's your water minus H2O. That comes out of the thing now. So now what you have now is these two monomers now joining together. So what I'm going to do, I'm just going to erase the middle section and join them together. All right, that's what I'm going to do. So I'm going to erase that and erase this. Okay, so now this now is your new bond right there. So this is now going to be bonded to that nitrogen. Okay, and as you can see here, this is the amide link. See, C double bond O bonded to a nitrogen, which is bonded to a hydrogen. And that's your amide link. Of course, over here, you can have another polymer being added, another monomer, and over here, you can have another monomer being added until you get your protein. Of course, you know, protein is needed for growth and repair. Your hair is protein. Your skin contains protein. If you're black skin or dark skin, let me say dark skin, not black skin. If you're dark skin, then your pigmentation, the melanin is protein, collagen is protein. All of these things are proteins. Okay, enzymes are also proteins. So this is how all of those things are made.
Sir,
Yes, someone has a question.
when if you're black, your melanin have protein.
What's that?
When if you're dark skin, your melanin has protein.
No, well, everybody has melanin, you know. It's just that white people are Caucasian people don't have that much protein. Their concentration is low. But people of color have a higher concentration of melanin, which is a protein. So melanin is what causes our skin color to be dark.
Also, melanin itself is a protein.
Yes, melanin is a protein, and this is how melanin is formed. The only thing is that this R, you don't know, you can identify this R in the melanin, whatever it is. I don't know what it is specifically, but we could identify that. All right, just like hemoglobin and all these other things. Okay. Any other questions? All right, so that's proteins, which is our second polymer. Now, the next one is fats. Fats are formed from fatty acids and glycerol. Okay, and these are polyesters. See it right there, these are polyesters. If they're polyesters, it means that they have the ester link or the ester bond in their structure. So let us look at what glycerol looks like. This is what glycerol looks like. COH, COH, COH. That's glycerol right there. Hydrogen, 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 hydrogen. Okay, some people in some books you may see 1, 2, 3 propane triol. Hold on 1 second. Okay, all right, so that's your glycerol. 1, 2, 3 propane triol. Now the fatty acids have a specific structure now, and they're acids, so they're gonna look like acids. So they're gonna have H, O, C double bond O, R. Now you notice that the alcohol, these are alcohols, as you can see. That's an alcohol, you know. See, OH, alcohol functionality or alcohol group. So those are all alcohols. Now you notice that there are 3 alcohol groups. When you react an acid and an alcohol, you get an ester. And this is exactly what we're doing. We're reacting an alcohol, which is glycerol. That's why the name is glycerol. Anything that you see with ol is an alcohol. All right, with the acids. Now these acids, notice I put R here, R1, right? That R can contain up to 27 carbon atoms. We're not gonna draw 27 carbon atoms for sure, all right? Then now there's another acid down here because you have 3 different alcohol groups, so then you have R2. Then you have another acid over here, which is gonna be R3. All right, so what happens now? It's a condensation reaction. So therefore, water is going to be removed. So you're going to take out your water. For those people who are here last week, you remember that I said the water is HOH, but the oxygen in the water comes from the acid. So this is it, like that. And this is your water that you're taking out, H2O, like that, you see? And so these 3 water molecules are taken out, and I'm just going to erase them, right? I'm going to erase them. And then what you have happening now is that the acid and the alcohol are joined together like that. So there you go. I'm just, because I don't want to erase and redraw, okay? So there you go. And this is what now, this structure that you're seeing here, this is what we call fat. This is fat, F-A-T. In some books, they call it lipids. All right, so that's fat or margarine, whatever you want to call it. Remember now, notice that these R groups are not defined. So these things can change the type of fat it is. Okay, and you can mix acids and create a weird looking fat or a weird fat. All right, this is, when I say fat, I'm talking about lipids like margarine, chiffon, butter, those things. All right, so that's your fat. And this is the polymer. It's a weird polymer because you'd say it's a weird polymer because it doesn't have this like repeating unit that you're used to seeing. Okay, so your regular polymer, you would see A bonded to B, then you have A bonded to B, then you have A bonded to B, bonded to A bonded to B. So you have this regular repeating unit. For this, you don't have that. You have glycerol, which is then bonded to 3 acid groups, and that's your polymer. It's a polymer because it's big, right? It's a polymer because it's big. It's a macromolecule. It's a big molecule, and that's why it's a polymer. Okay, so that's your fats. For your next one, which is the carbohydrates now. Oh my God, I totally forgot that. Sorry. Notice that in the fat, you had this bond here. You had carbon double bonded to oxygen, bonded to the R, bonded to the oxygen, bonded to the glycerol, which I'm just gonna leave like this, right? Bonded to your glycerol. So here is your ester link. That's your ester link right there. Your examiner may ask you to recognize it and highlight it and name it. That's why I'm pointing it out. They like to do those things. So that's your ester link in your fat. Okay, so let us proceed again. The next one is your carbohydrates formed from monosaccharides. I said mono means one. The word saccharides means sugar. So it means one sugar, or in biology, they may call it simple sugar. These are polyethers or polysaccharides. So many ethers or many sugars. That's what poly means, many. So what does this look like? Now, because there are many different sugar molecules, right? Many simple sugar molecules, they tend to just simplify your monomer for the sugar. And what they tend to do is use something like this, HOXOH. And that's one monomer, right? And then they're going to join that to another monomer, HO. Let's just put YOH. It doesn't matter, it could be X still. Okay, and so of course, this is a condensation reaction again. Take out water. So that's what you're gonna look to take out, the water out of this. So here we go, we're gonna take out water. It doesn't matter how you take it out, just take it out. And the water goes there, minus H2O, right? And what you're now left with is this oxygen is gonna be bonded to the Y. So this is what you're gonna be left with now, right? After we take out our water, this is what we're going to be left with. HOXOYOH. And of course, you know what? Let me change back that Y to X. Change the Y to X. So there it is. And of course, you can take another HOXOH and attach it over here, and take another one and attach it over this side. And you continue to add to the chain, continuously adding to the chain, okay, until you get to your polysaccharide. All right. So we will proceed again. Now it says questions now define condensation, the combination of two molecules to produce a larger molecule and a small molecule, which is usually water. All right, then define hydrolysis. Hydrolysis is the breakdown of a polymer using water. Okay, so look at the word here, hydrolysis. The word hydro means water, H2O. The word lysis means to split. So hydrolysis means that water is being used to split. In the context of polymers, we tend to say that water is splitting the polymer. Okay, so that's pretty much condensation and hydrolysis. We're going to look at the splitting of the molecules soon. So down here now, it says, give one difference between the properties of the monomer and the polymer for the above named polymers. So give one difference between a monosaccharide and a polysaccharide. Monosaccharides are usually simple sugars. They tend to be soluble in water. Polysaccharides tend to not be soluble in water. Okay, so that's one difference. Fats, for example, fatty acids and glycerol. Fatty acids tend to be, partially soluble in water again, and glycerol may be dissolved in water, may mix with it a little, may very little. And the polyester, the fat now, is large, it weighs a lot, and of course it is not going to be soluble in water. For the next one now, proteins, same thing. You can look at the solubility of the thing in water, and that's a good one to always look at. Okay, Give two uses each of the above named polymers. What are proteins used for? Proteins are used for growth and repair. We mentioned that already. Polymer fats are used for storage. They're used for insulation in the body. Proteins are, yeah, we mentioned that. Sugars are used in respiration, right? And nylon is used as a fabric. Okay? And that's that. Look, now we're going to go down to hydrolysis now. So the hydrolysis of a polymer into its monomer units using water as a breaking agent is called hydrolysis. That's what hydrolysis is. So you have protein hydrolysis, you have carbohydrolysis, and you have fat hydrolysis. And we're going to look at all of them now. Okay, so I'm first of all going to draw the protein. All right, I'll draw the protein. So this is what the protein looks like. Remember, proteins are polyamides. Polyamides has this link in them, carbon double bond, oxygen bonded to a nitrogen, bonded to a hydrogen, and then this is going to be bonded to a carbon, which is bonded to a hydrogen, and an R group there. Then you have your C double bond O, OH, and over this side now you have carbon, which is bonded to a nitrogen, bonded to a carbon, which is bonded to a R group, which is bonded to a hydrogen, which is then bonded to a nitrogen, which is then bonded to a hydrogen and a hydrogen. So we're looking at the hydrolysis of this species now. So water is going to split the species. The species can only be split into what made it into the first place. Okay, that's all. It can only be split into what made it. So if a protein is made up of 2 amino acids, it's going to split into the 2 amino acids. So the question is, where does it split? It actually breaks right here by the amide bond. Okay, so that's where it would break down. And you get back your 2 amino acids. Now, over on this side, you'd end up with a H, and over here, you'd end up with your OH. So there is your amino acid on that side. There's your amino acid on that side. Okay?
Yes,
Right.
sir. Yes.
All right. So next one is the carbohydrate hydrolysis. Pretty much the same idea. It's the same idea that we're running with. You have your carbohydrate, which we're going to draw as HOXO XO OH. Okay. Okay, yes. And watch this now. I didn't mention this, sadly, but this is the ether link in the carbohydrate. This is the ether link, right? Remember I said that carbohydrates are polyethers. Let me go back up a little bit to show you, but I didn't mention it. See it right there? They're polyethers right there. But you're not seeing that. Yeah, right there, polyethers. And this is the ether link, XOX. So, of course, if it is that you're going to hydrolyze this, you're going to break the bond somewhere. You're going to break the bond somewhere right here, and you're going to end up with HOXOH. And then on the other side, you're going to have your OH right there, XOH. So this is supposed to be H, not that. Right? So that's how you're going to end up with your 2 monomers. Okay? And that's the hydrolysis of that. We want to get to the hydrolysis of fats because that is important. Okay, so we go back down here. Now is the hydrolysis of fats. Remember that your fat is made up of fatty acids and glycerol. So this, I'm going to draw the glycerol bonded to the fatty acid, R1. And those are hydrogens, that's carbon, oxygen bonded to that, R2. Then you have your carbon again. We're not drawing the hydrogens, really, because those are not that important, R3. So of course, with hydrolysis, we're gonna break the ester link, which is right here, right there, right there. All right, now when you break your ester link, you're gonna get your acid over here. So this is gonna become OH, and this is gonna become H. So over here now you get back your glycerol. Now, something that I want to mention about the fat hydrolysis. Hydrolysis may occur in 2 ways. You can have alkaline hydrolysis. I'm sure I did this last week. You can have alkaline hydrolysis where you use an alkali, such as sodium hydroxide or potassium hydroxide, right, with the water, and you heat, or you can have acid hydrolysis, where you have an acid such as HCl in the water and you apply heat. Now, when you do the acid hydrolysis of fats, you end up with your glycerol and the fatty acids. Okay. However, when you do the alkaline hydrolysis of fats, you end up with, instead of the acid, so I'm going to clear something over here so we can look at that. Okay, so what you would expect to get with the hydrolysis of the acid is this. You are expected to get this RC double bond OH. But when you do the alkaline hydrolysis, you don't get that. What you get is RC double bond ONA, which is coming from this, the hydroxide, the sodium, or it could be potassium too, or it could be magnesium. I hope you get what I'm saying. But instead of this being hydrogen, the hydrogen is replaced by a metal. So you end up with a salt. So this is actually a salt, you know, believe it or not. So that's a salt. Now, this salt, they found out, can be used to clean clothes. So they call it soap. So this salt is actually soap. And so because this process of the alkaline hydrolysis of fats produces soap, they call this process saponification. And I'll clear all drawings there. Okay, they call it saponification. And what is saponification? This is the alkaline hydrolysis of fats. That's what it is, the alkaline hydrolysis of fats, okay? And the alkaline hydrolysis of fats produces a salt of the acid, which is soap. All right? Clear?
Yes, sir.
Okay. What I want you to do, just a little research now, is the very last thing is this thing. I want you to look at soap, soapy, and soapless detergents. Just look for those things online. Here's what you're going to look for. You're looking for how they're made. So making and advantages and disadvantages of the two things. What's the point of me using soapy detergents? And why should I not use soapless detergents, for example? Okay, that sort of thing. What is the good things about them? All right, is that clear?
Yes, sir. Should we do this now or for next week?
No, you're not gonna do that. No, not next week. You don't have time next week. You're gonna do that when we're finished here. Okay, I'm gonna try and pull up some questions now. Let me see if I can find them. All right, watch this now. This is a past paper question, as you can clearly see. This is in June 2021. All right, as you can clearly see there. Now, this is actually a reaction scheme. And I'm just going to show you what we're talking about when you look at organic questions, right? So it says figure 3 refers to the following reaction scheme. Notice it's a scheme involving 4 compounds, A, B, C, and D. Carefully consider the reaction scheme in figure 3 and answer the questions that follow. Now, the critical thing about any reaction scheme is the central molecule. All right, so your focus should always be on that molecule and how it is being transformed throughout the process. All right, so this here right here is your focus. So when you look at compound A, you recognize that compound A is an alkene. It has a carbon-carbon double bond. All right, something happens and you change carbon 1 into carbon A, compound A into compound B, which is that one. Something else happens and it changes to C, and you do something to it and it changes to carbon dioxide and water, and then you do something else to it and it does something else. It changes into this weird looking thing. All right, so one second. All right, right. So it's and we're gonna look at this thing first before we even go into answering the question. Now notice the difference between compound A and compound B. Compound A has 2 hydrogens, well, 3 hydrogens, and compound B has 2 more hydrogens than compound A, which means that you have added 2 hydrogens to compound A to change it to compound B, which means that this is a hydrogenation reaction. Remember, we looked at reactions of organic compounds. So this is a hydrogenation reaction. Now let's look at 2. For 2, compound C, you'll notice that compound C has 2 bromine groups attached to it, or 2 bromine atoms attached to it, which means that you would have added 2 bromines to this. Now, because you're adding bromine and bromine is in group 7 and group 7 elements are called halogens, this is a halogenation reaction. All right. Then now let's look at compound 3, reaction 3. For reaction 3, you have done something to compound A and it has been converted to carbon dioxide and water. Now, if you remember when I was looking at reactions of organic compounds, the first reaction was always combustion, where carbon dioxide and water was produced. So this is a combustion reaction. Then we just did this actually. Notice, I remember when I drew the square brackets a while ago and put the N outside. This is a polymer. Okay, this is a polymer of this over here. So this is polymerization and additional polymerization at that. So let's look at what they're going to ask you. So it says identify the types of reactions numbered 1, 2, 3, and 4. We have actually just done that. Reaction 1 is hydrogenation. Reaction 2, halogenation. Reaction 3, combustion. Reaction 4, polymerization. All right, you see that. Okay. And that's all they asked you for there. Let's see if I get the other question. Hopefully this is it. This is not it. But okay, fine. We look at the question. So here's another question. Ethanol is widely used as a solvent for making cosmetics and perfume. That's ethanol right there. This is some molecule D. State the name of compound D and identify the reagents and conditions necessary for ethanol to be converted to compound D. So now what they're really asking you is this. This is ethanol. This is, you should recognize as ethanoic acid. How on God's green earth am I going to convert ethanol to ethanoic acid? Now, if you remember when I was going through the reactions of organic chemistry paper that we were going through, I said you must know reaction conditions, because they will ask you about that. Lo and behold, they're asking you about it here. When was this? June 2020. June 2020. So you would have to know, say, how do I convert an alcohol to an acid? Well, it's not so bad. What you're going to do really is oxidize the ethanol. And how do you oxidize it? You're going to use acidified potassium permanganate in a little heat. The triangle means heat, and that's how you do it. That's all. You heat the ethanol in some acidified potassium permanganate for a long period of time, and then you're going to get your acid over there. So look at it now, state the name. You're going to get 1 mark for stating the name. And then for identifying the reagents and conditions, the conditions is a little bit of heat, right? The reagent would be this. So that's where you'd get your 3 marks. Okay. So you have to know those things which I had mentioned to you guys. I did a video about reaction. What I did was I took all the organic chemistry questions I could find from recent past papers and I answered them, put them in a video, and I sent it to you guys. You need to be watching those videos. It's critical. Okay, so we're gonna stop there for today. Hold on, I will say this in the group because our time is gonna be up shortly. Okay, I'll send a message in the group. All right, guys?
Yes, sir. Bye, sir.
Okay.